something you had to earn, you had to work at tutorials. You didn't sit there and just like press on something that was done for you. So this is how this tutorial is going to be. Everybody's going to open a Jupyter notebook. I'm going to go through code that I've already written, but I'm not going to show you what's next. You're not going to know what's next. You need to write the next steps. They're all simple. It just uses NumPy and matrix operations, but I'm going to ask you questions and you're going to show me your answers. You're going to answer questions, etc. Okay? Just because this is the way that I was taught tutorials to go. At another point, if anyone wants to work with this one, and we have other code that is better written, but I can't share it yet, simply because of the fact that we haven't published it yet, so I can't share the code before we publish. But if you are super excited about some of this, come talk to me. You can talk about how you want to use it for your particular experiment. This one is for our Plus computational biology paper. So it has SR-DYNA with various kinds, SR-MB combinations, SR-DYNA with TD, etc. to solve 3-4 different reinforcement learning problems, including problems in our paper and problems from other people's papers. So if anybody wants to practice SR-DYNA there, that's good. But for the time being, what I decided to do is very inspired by how Eshin and Emma reacted to what I was telling them on the board yesterday. There was a point where they were all like, oh, they got it, and then they started generating new ideas. So if it's okay with you, whoever can do it, I would ask everyone to do it, but at the end, just raise your hand if you, after the tutorial is over, and tell me how you think this could be applied to your research, because I think it can be applied to a lot of people's research. Okay, so you just need NumPy right now. Just import NumPy as NP on your Jupyter notebook. And this is what I'd like to ask you to. Oh, great, I broke it. Can I not do this? I have to do this. I have to do this.
Oh. Otherwise, we can't hear you at all.
Oh. Okay, so I'll draw a MTP on the board, a Markov decision process, which means it has some states and it has some transition structures, which is basically circles and arrows. And I'll ask you to create a NumPy array that looks like that. Okay? Is that good? Is everybody on board? What we're going to do? Okay. So here it is. You have state 1. It goes to 2. It goes to, actually 3 here. It goes to 5. And it goes to 7. Let's start with the smaller one. So just goes to 5. And then, this is 3 by the way, everybody. Odd numbers. 2 goes to 4, goes to 6. So do you know how to turn this into an array, into a matrix that shows it? Everybody knows, everybody's on board? Okay. Yeah.
We should just create a matrix with position 1, 3 would be a 1, and then 3, 5 would be a 1, and everything else would be zeros.
Exactly. Cool. So it's a 6 by 6 matrix, and you just put a 1, so the probability of transition at this point for ease of use is 1. Okay? This is also known as an adjacency matrix, which in this particular case is the same as your transition probability matrix because the probabilities are 1. But in other cases, the adjacency matrix and the probability matrix are not necessarily the same. Has everybody got it? Everybody has it? Who doesn't have it? So for people who are actually going to do a tutorial, who doesn't have it? Okay, I'll wait.
Can I actually ask a more detailed question?
Sure.
There's a probability between 1 and 3, between 3 and 5, but is there anything implied between 1 and 5, or does it always have to go by 3?
So that's what we're going to get at.
Okay.
But for just the adjacency matrix, you would only have the one-step transitions. Also, so adjacency matrix in graph theory and also probability matrix in reinforcement learning, or transition matrix, which is called T or P, all of them only consider one step, which is the Tolman style that we were talking about earlier. Okay, everybody got this? It looks like this. Yeah.
Should we do it as an array, or should we do it as an NP dot matrix?
However you want to do it,
Either way is fine.
that you can follow the tutorial.
Cool.
You're going to do matrix multiplication yet later. So okay, now I'm going to ask you a question. For those of you who don't know the answer already for a very long time, what happens if we multiply this matrix by itself? No, don't do it. Don't do it yet. Hey, smart guy. Okay, what happens if you multiply this matrix by itself? Any guesses? Okay, those of you who know it already, other than mission, or
Identity matrix.
what's that?
You get identity.
No, but thank you for answering. Anybody else? What do we get if we multiply it twice? Okay, Shin, you want to go?
Yeah, like unraveling one time word.
Can you say that in English?
The second step of the marketization process. The second.
Okay, so everybody multiply it by each other. Multiply the matrix by each other.
So you have to use the dot product.
Dot product,
not
yes.
element-wise.
Yes, so it's NP dot parenthesis maze maze.
If you're using Python 3, you can use the at symbol too. It's a new addition. Python 3. Ooh, fancy.
Wait, what symbol?
The at, like my name at Gmail. Yeah, that's it.
Okay.
Wait, it just.
You get a chalkboard for that.
Yeah, matrix
That's
at.
awesome.
Matrix at matrix. Yeah, that's matrix.
Did you notice you got brownie points?
Oh, yeah.
Twix points.
This is why we doctrine.
Okay, so, you do add equals, like.
Okay, did everybody do this?
Python 3.
Did everybody do this? I'm sorry, I did it the old-fashioned way.
Oh, that's cool.
Okay,
Yeah, not the same.
so can someone tell me, for instance, okay, you don't have I think it's best if I ask you because you don't have a laptop. So,
Couldn't be happier.
so, what is happening here? What do you see here? How is this different from last? What did we learn from this? What are we learning here?
It's essentially,
So let's look at row 1. Compare row 1 of this one. In order to hide the things, I've made this so huge.
so it essentially was answering the question I was asking earlier
Exactly, that's why.
about if it's able to jump. But
So,
what's confusing to me,
tell me what's confusing.
because I don't do matrix multiplication in my head well, is that I would have expected only to be able to get one element where there was previously a one in the matrix. And essentially, that's not true in this case. So I would have only expected like where there were overlaps in the sequence.
I don't understand the algorithm that you're describing, but I just want to go this far to say when you multiply that row, which says there's a relationship between 1 and 3, by basically by the whole entire matrix. What happens is that you find out that within 2 steps, there is some other node that is connected to 1.
What in the second matrix tells you that it's in two steps? Is it
The
because
second matrix doesn't tell me that it's in 2 steps. The second matrix, I know it's in 2 steps because I multiplied it twice by each other.
Right.
But the second matrix tells me there is a relationship that I didn't have in that one.
Right. Okay.
So for instance, and that relationship is between, for instance, 1 and 5, and there's another one. Everybody can see the other one as well?
Okay.
2 and 6. So basically it says there are connections here if I multiply the matrix 1 time by itself, meaning it's 2 steps into the future. Does that make sense? Okay, now, where did I? Okay, now, if we do it another time, what happens is that we don't get anything else. Why do you think that is? We get zeros next time.
Because you reach the goal state.
Because we don't have anything deeper than 2 levels. So if we have matrices, this goes on and starts becoming 0 when you reach the depth of the matrix. So matrices that are shallow, they're going to have lower number of things. But if we added something like this, and we added like something like this thing will go on forever, right? You could basically stay on this maze then forever and ever and ever. So do you guys want to do that? Just make now this matrix. And then multiply it 3 times by itself and tell me what happens. So you see, without increasing the number of states, by just adding, honestly, by just adding 2 connections, we created like an infinitely deep matrix. Does that make sense to you? But this is not an absorbing Markov chain. Does anybody know what an absorbing Markov chain is? Anybody want to raise hand? Oh, you know, you've been in botanic lab. You're not alone. Anybody who's not from a botanic background?
It just converges to some final state.
Which is like what?
Or some neighborhood state. Like it gets a probably 1 at some state like that.
Right. So for instance, if it had something like, let's say it had something like this with some probability, it will get into this sort of state, and this was 1. This is the final state. You've gone there and you can't move anymore. This is the math botanic used to explain this as death. It's like you die here. You just can't go back. So if you do this and you start multiplying it by each other, you will figure out that you keep finding more and more and more connections, right? Did everybody do that? You'll figure out in how many steps you will reach one point starting from what point. You've seen that, right? Everybody did it? Okay. So this is interesting. Why is it interesting? What do you think this has to do with the successor representation I was telling you? What are your guesses? Any guesses? So the successor representation was this idea that you can store information about what are the things that you're going to visit many times in the future, right? And so if things had a connection with each other, you would expect to visit them more often. But because you're myopic, you think things that are closer to you are more likely and exponentially less expecting things in the future. So that's the planning horizon we're talking about. That the gamma that is between 0 and 1 says how much you're going to squint your eyes to see the future or not. So let's add a gamma. Let's add that kind of thing. And let's say that the gamma is 0.3, and you are going to have, just like add a gamma. And see what happens. All right, okay. So all that happens is that, and this again goes back to a question that was previously asked. Now, assuming you know that the adjacency matrix or the matrix has a probability of 1, you reach here and it's less than 1, you realize this is some steps away. If you know what the gamma is, you can tell how many steps away because it's an exponential sort of relate. It has exponential relation to gamma. Does that make sense?
When you say sub-steps away, you still mean that it's like contained within the size of that matrix, but that you have to continually sample those points? Is that what you mean?
Let's say you took infinite walks on these matrices. You just took infinite random walks on this matrix over and over and over. And every time you use a discount factor. At some point you'll figure out that, all right, I expect a certain number of times to end up somewhere. I expect a certain number of times to end up somewhere. And whatever probability of transitions are gets multiplied by this discount factor that exponentially decreases over time. Because I'm multiplying something that is between 0 and 1 by itself. It goes like this. That's this kind. This kind of thing. Just inverse. And then you have discounted average expected future occupancy. It's like I think working memory capacity ends at some point. So it's discounted. It's mean, average. And what is it? The unit is expected future occupancy. How often am I going to see this again? On average, given I have some discount. Okay, now, you can make a larger matrix, you don't have to do that now. Just like go back to this thing. So can you guess right if, let's say we started adding the gamma from step 1, and we started adding every step together. Can you write that and figure out what it is? Meaning you have gamma times your matrix plus gamma squared times your matrix plus gamma to the power of 3 times your matrix, What do you think will happen? So do that and just tell me what that leads to. Does everybody get what I'm saying? No? Who gets it and who wants to explain it? Jeremy.
Well, does someone else want to explain? Eshin?
Yeah.
That's how work gets done. Yeah, you just delegate now. Eshin, did you want to explain?
You volunteer, Eshin.
Yeah, I mean, it's just the long run average taking into account the discount factor. And then so you just get an average representation at each from the transition matrix, expand it out to whatever time points until it resolves, taking into account again.
Does everyone understand what Eshin is saying? Does anyone want to put it in another word? Or in other words? Multiple one, not one. One word actually would do it. No, 3 words. 3 words would do it. It's like sum over future, right? So if you do this, for every row you will know what is in the future of 1, including loops, which is beautiful. And what do I mean by that? If there was a way that I went from 1 and after 3 steps I reached 3, but then or like 5, but then from 5, step 4 I went to 2, step 5, step 6, step 7, step 8, step 9. Which means that I would have visited 5 from 1 different times with different discount rates. 1 time with gamma equals gamma to the power of 9, 1 time with gamma to the power of 3. Does that make sense, what I'm saying?
I'm still struggling with the concept of a discounting rate. So,
Have you heard the term discount rate before? In what context?
like in a sale.
In a
Like,
sale?
how much of it is discounted?
What about temporal discount? What about the notion that something with time, there's a discount parameter that discounts things with time? Actually, we can use it in the context of sale. Let's say that something, its value dropped the longer it was there. It's meat and it's going to go bad. So you got to at some point put it on sale and at some point you just got to put it on cash. It's going to reach 0. So it starts somewhere and there's some function of how its value drops to 0. One way to construe this drop in whatever it is over time is to look at it in terms of discounts, right? So when you want to think about things that change with time, exponential sort of relations are extremely useful. And for many reasons that I can't even begin to talk about now, but when you do various kinds of logarithms, integrals, etc., they're just wonderful. They save your life from confusion. So that's one way to think about it. Another way to think about it is, can you remember what you ate yesterday for lunch? Oh my God. Can you remember what you ate today for lunch? Yeah. Okay. Can you remember what you ate last week today for lunch?
No.
Can you remember what you ate yesterday for lunch?
Probably.
Okay, so you see there was yes, probably no. So you had another kind of thing. Now, probably this wasn't the explanation, this was more sharp than I thought. Maybe your gamma was very low. But the point is that time does this thing when we want to think about the past, or we want to think about the value that drops. Now, if I ask you, what are you going to do tomorrow? You have some idea. What are you going to do in 5 years? So that's the way that we can see further things in the future as well as we can see things that are now. So when you figure out that today and yesterday and the day before you saw me, you don't have to imagine that you're going to see me in 5 years because you don't know how much you can extrapolate from your memory to what's going to be predicted in the future. But tomorrow you're probably going to see me again. So for a short time horizon, you have a better idea of what's in your future, what prediction you can make about what you're going to visit. But for a long-term time scale, it's more difficult. And that comes back to this horizon that I was talking about. So do people see what's here or should I draw it there? Do people see this? Okay, sure.
These people want to say.
Do people from there see this? Okay. So,
Those boards go too bad if you want to keep multiple. There's a button.
There's buttons there. You can move.
There's words on it.
I have space, but Nice. Okay. So this is your gamma, which is your discount rate, and it's always a value between 0 and 1, can be equal to either. And then this is, let's say, your predictive horizon. This is not a term, I'm making this term up, prediction horizon, okay? Horizon is a term, you can use it for planning horizon, a lot of different kinds of horizons. Okay, so let's say these are how many days from now you're going to remember things. So if your gamma is small, you get something like this. If gamma gets larger, you get things like that. So these are horrible, I'm sorry, I apologize to anyone who's ever done this. These are horrible exponential curves. But now you see what I'm talking about. So if you have a smaller gamma, you can see this many steps into the future. If you have a larger gamma, you can see that many steps into the future. It should make like, imagine that this is like very much fine scale. Okay? Does that make sense to everyone now? Is everyone clear about like so the further things are in the future, the more discount. And one way to do that, if you have a value between 0 and 1 and you keep multiplying by itself, you get this. And that would look like this. T is the time step that